Calcium is released from the site of the sarcoplasmic membrane. Here, it's represented as our film. Next, calcium will bind to the troponin. The troponin will change its form and disconnect from the active sites on the thin filaments, or the actin, allowing the myosin heads to bind. So this model represents the process for muscle contraction in striated muscle. This is my model of the sarcomere. First, the I band, as you can see on this form right here, the I bands will be, you have the Z line on this side of it. Your I band will extend just past your Z line and is represented through foam board. Now, titin. Titin is the huge protein. Its function is to act as a molecular spring. It's a source of elasticity in muscle, and it's important in the contraction process of striated muscle tissue. Actin, or thin filament, here is represented through our yellow pipe cleaners. Their function is to interact with the myosin to produce a force, to regulate the force generation in response to our calcium, our Ca2+ concentration, thereby transmitting force to the ends of the cell. Tropomyosin is our next component. It is represented as our orange pipe cleaner. Here you can see that it is wrapped around the thin filament, or the actin. Its function is to prevent the myosin from touching actin. So next, on or in the whales, if you will, of the tropomyosin is our troponin. So troponin is a tri-unit protein. Here it's represented using small pom-poms. There are three types of troponin, which is why it is known as a tri-unit protein. There is troponin T, troponin I, and troponin C. Troponin T acts to retain protein to tropomyosin. Now, troponin I should act to prevent our magnesium that is going to be triggered by our ATPase process, and then will bind to troponin T and troponin C. There it will separate and the combined troponin units from being drawn towards the site of our actin, or our thin filaments. Troponin C, its job is to allow calcium source to be brought into muscle. The next component of thin filaments is going to be at the end of our thin filaments. Here it's represented through a purple pony bead. This is known as our tropomodulin, or our TMOD. So in the TMOD, isoforms TMOD1 and TMOD4 will interact with our lyomodin, our LMOD2 and LMOD3. This will control our myofibril organization, or the way that our myofibrils are collected. The thin filaments length and the actin-myosin cross bridge will also be controlled through the TMOD process, along with the formation in our skeletal muscle fibers. Alpha-actinin. Here, as you can see on both sides, it is represented using a red silky cord. It's going to support our Z line. It's going to be a cytoskeletal protein that creates the Z line and holds the thin filaments within that site of the Z line. We are going to assist with the control of the length and tension in our stress fibers. And the last component in our Z line, or our I band, is the nebulon. Here it is represented using the green pipe cleaners. Nebulon starts on the Z line, and it moves across the I and the A band, where it's anchored or stops in the M line or the H zone. It is going to determine the length of the thin filament, and it acts as a ruler. So the nebulon's job is to act as a ruler for determining the length of our thin filaments or our actin. The H zone, as you can see here, it is this site right here. It's the area of space within our thin filaments in the A band, which the A band is represented here. The pseudo H zone, which is the very center leading up to the M line, is going to be where there's going to be no myosin heads present. The M line, or that center, is going to be the force that prevents our thick filaments from falling off track and colliding. The thick filaments are represented using a 1/4 inch threaded rod. The 1/4 inch wing nuts on the threaded rod are our myosin heads. Now in myosin is made up of 6 chains, 2 heavy chains and 4 light chains. The site of the light chains is going to be where our actin binding site is, and also where our ATPase process will happen. The twisted copper wire on the thick filaments are our C proteins. The C protein's job is to keep the thick filaments together. It is dissected by calpain for the process of muscle turnover. The thick filaments will overlap here with our thin filaments with the use of these C proteins. So the movements. On this specific model, our movement is done by our popsicle sticks in a skiing motion. On the actual sarcomere, the contraction will take place Z lines. So our Z lines, which are these right here, the light blue on the foam board, are going to move together. Our I band, which is an outside parameter of our Z lines, will also shrink in size. The A band will stay the same width. Now, when fully contracted, the thin filaments will cross each other. And the last thing that I'll leave you with, without the sarcomere muscle contraction, would be next to impossible. Thank you.